Hi, Assalamualaikum and a very good morning. So today we're going to do some tutorial discussion for chapter 6 and we're going to focus on the subtopic of 6.2 equilibrium constant in which we're going to solve the Kp, Kc and using the ice table. Next, we're going to also look into the subtopic of 6.3 which is the Lee-Chatelier's principle. So we're going to do tutorial question 8, 9, 10, 11, 12, 13, 15 and 16 respectively. So without any further ado, let us start. So for tutorial question 8, 1.00 mole each of the carbon monoxide and chlorine gas are introduced into an evacuated 1.75 liter flask at 668 Kelvin. At equilibrium, the total pressure of the gaseous mixture is 32.4 atm. So we have to calculate the Kp. So the equation is given as here, which is the carbon monoxide gas reacting with the chlorine gas in order to produce 1 mole of COCl2 gases. So we have know that CO and Cl will have 1.0 mole each. Okay, and we also know the volume as well as the temperature. Okay, so from here, the idea that we gonna do is we need to calculate the Kp. So for this reason, we need to do the ice table because we need to get the partial pressure at equilibrium. Okay, so we're going to do the ice table, which is ICE, initial change and equilibrium, which refers to the ATM, in which it is referring to the pressure. So for the pressure, we need to find the initial pressure where we can obtain it by the value that we got here. We have number of mole, volume, as well as the temperature. So as what you can see here, we can get the initial value by doing the ideal gas equation, which is PV is equal to nRT. So now let us focus on the carbon monoxide first. So PCOV is equal to NCORT. So we need to find the partial pressure of carbon monoxide at the initial stage. So the number of mole of CO is 1, and then our R here is the gas constant, which is 0.08206, and then the temperature is 668 Kelvin, and then our volume will be divided into that, will be 1.75 liter. So mole, here is liter atm per mole per Kelvin, and then here in Kelvin, and then 1.75 liter. So liter and liter going to be cancelled out, per mole and mole going to be cancelled out, Kelvin and per Kelvin going to cancel out, so we're going to get the atm. So once we do the maths here, we're going to get the value at the initial stage of the partial pressure of the carbon monoxide going to be 31.32 atm. And since the number of mole of CO and Cl2 are the same, so we can say that the initial pressure of both of them going to be 31.32 atm. So now we have obtained the initial partial pressure for both of these reactants. So we're gonna plug in the value here, which is 31.32 and then 31.32, and at the initial stage, the product here gonna be 0. And then as time goes by, the partial pressure of the CO and Cl2 will decreases by X pressure. Okay, so the stoichiometry here is 1, so it's equal to minus X. For Cl2, it's going to become minus X, and then for COCl2, it's going to become plus X because product increases by time, and then the reactant going to be decreases by time. So at equilibrium, 31.32 minus X here, we're going to get 31.32 minus X. Similarly goes for the chlorine gas, 31.32 minus X. And then for COCl2, we have X partial pressure at equilibrium. Okay, and as what you know that, it was mentioned that at equilibrium, the total pressure of the gaseous mixture is 32.4. So we can say that total pressure is 32.4 atm, and then this partial pressure at equilibrium add up with 31.32 at equilibrium, add up with this one at equilibrium is equal to 32.4. So we're going to add all of them together, and then we're going to settle the maths here first. So you're going to get 63.64 minus X. So we need to find the value of x here. So once we do the maths, we're going to get the value of x is equal to 30.24 atm. And hence, we can now obtain the partial pressure of each species at equilibrium. For example, for COCl2 is equal to x, where x is equal to 30.24 atm. For Cl2, it's going to be 31.32 minus 30.24. And hence, once we calculate that, we're going to get 1.08 atm. Similarly, for the partial pressure of the carbon monoxide, which is 1.08 atm. So the question asks for the Kp. So the Kp is equal to the partial pressure of COCl2, which is the product, to the power of 1. So usually number 1 here is ignored. And then divided by the partial pressure of the reactant. So PCO as well as PCl2. And then we're going to substitute the value of the partial pressure here. So this one, please use the rounded bracket. And then for PCOCl2, we're going to get 30.24 divided by 1.08 and then divided by 1.08 as well. So once we do the maths here, we're going to get the value of Kp to be 25.93 without any unit. Okay, because in this chapter, we're going to assume that Kp and Kc is dimensionless. Alright, so that's all for tutorial question 8. So for tutorial question 9, the ammonium hydrogen sulfide decomposes at 250 degrees Celsius according to the reaction of NH4HS solid converted to the ammonia gas as well as the H2S gases. The Kp is given as to be 0.110. So if 55.0 gram of solid of the NH4HS, which is the ammonium hydrogen sulfide, is placed inside a sealed container of 5.0 liter, so we need to find the partial pressure of NH3 and H2S at equilibrium. Okay, so this is a decomposition reaction, and this follows the reaction as shown here. Alright, so since we need to find out the partial pressure of the ammonia as well as the hydrogen sulfide at equilibrium, then we need to use the ice table. So we need to write the equation once again, which is NH4HS converted to NH3 gases as well as the H2S gases. So ICE, initial change in equilibrium, and since we are talking about the partial pressure, then the unit here need to be in the unit of atm. And then for the NH4HS, even though the value is given, but it is not going to be inserted into the ice table because it is in the solid state. So for the solid state, we're just going to ignore, and usually we just put it with a dash here. Okay, and for the information for the gases here, we know that at initial stage, there's no going to be any pressure for the ammonia as well as the hydrogen sulfide. So it's going to become 0 as well as 0 here. Okay, so you can imagine as the situation to be something like this. Let's say if you have a container which is 5.0 liter, and then you have a solid which is NH4HS. So at the initial stage, there no gonna be any decomposition. NH4HS ni tidak terurai untuk membentuk gas. Jadi pada mulanya, the partial pressure of both ammonia and H2S gonna be 0. But as time goes by, the solid will started to decompose. It started to produce NH3 and then it started to produce H2S. So the change here gonna increase by plus X as well as plus X. And then at the end, when it reaches equilibrium, it's gonna have the initial plus the change gonna be X as well as X. Okay, and from here, we need to find the partial pressure of NH3 and H2S. And in order to do that, we can use our Kp here. Okay, since we know that our Kp is equal to the partial pressure of the NH3 at equilibrium multiplied by the partial pressure of hydrogen sulfide at equilibrium. And then for the solid, we're not gonna include that in our KP expression. Okay, kita hanya abaikan solid. And we know that our PNH3 is equal to X at equilibrium. Similarly for the hydrogen sulfide. So X minus X multiplied by X, and then our KP is 0.11. And then we do the maths here, which is X2 is equal to 0.11. And X is the set of 0.11. So we're going to get X to be 0.33 atm. Okay, and then you need to do the conclusion in which the partial pressure of ammonia at equilibrium is equal to X, where X here refer to 0.33 atm. Similarly for the hydrogen sulfide at equilibrium, which is equal to X, which equal to 0.33 atm. Alright, so that's all for tutorial question 9. So for tutorial question 10, the bromine gas is allowed to reach equilibrium at 128 degrees Celsius according to the equation given here, which is the bromine gas decomposes into two bromine atoms, which is in the gaseous state. The Kc is given to be 1.1 times 10 to the power of negative 3. So if the initial concentration, so here is the keyword, of the Br2 as well as the Br atom to be 0.063 molar and 0.0112 molar respectively, we need to calculate the concentration of this species at equilibrium. Okay, so the initial one is given, which is Br2 0.063, Br going to be 0.012 molar. So in order to find the concentration at equilibrium, we need to do the ice table. So we need to write the equation once again, and then we have our initial, change as well as the equilibrium. And then molar refer to the concentration. So at initial, the concentration of the bromine gas is going to be 0.063. And then at initial stage, the concentration of the bromine atom going to be 0.012. As time goes by, the concentration of the reactant will reduce by minus X. The concentration of the product, which is the Br atom, going to increase by 2x because the stoichiometry here is 2. So it's going to increase by 2x. And then at equilibrium, 0.063 plus minus x, we're going to get 0.063 minus x. And for here, 0.012 plus 2x. So this is the concentration at equilibrium for both of these species. And in order to calculate the concentration, we need to find the value of x first. So we know that our Kc is equal to the concentration of the product, which is Br square, divided by the concentration of the reactant, which is Br2. So from the Kc here, we need to substitute our value of Br. So Br at equilibrium, it's 0.012 plus 2x, and our Br2 here is 0.063 minus x. And then Kc is also equal to 1.1 times 10 to the power of negative 3. So now we substitute the value. So 0.012 plus 2x square, so don't forget the square. And then Br2 is 0.063 minus x is equal to this value here. So this part here, we're going to bring it to the left-hand side. And then we're going to make it, once we multiply that on this side, and then we're going to bring it to make a quadratic equation. So ax squared plus bx plus c is equal to 0. Okay, so when you put it inside your calculator and solve the quadratic equation, you're going to get two values. So you get x is equal to negative 1.78 times 10 to the power of negative 3. And then you're going to get x is equal to negative 0.01050. So both of this value is negative, but we should take the less negative. So less negative value is taken. Okay, and this one, okay, so you can imagine it to be like 0 here, right? So negative 1.78 times 10 to the power of negative 3 is less negative compared to negative 0.010. 0.0150. So we need to take the value that's closest to 0. So more positive is better. Okay, but in this case, we got two negative values. So we need to take the less negative, or we can say we need to take the more positive value. Why is that? This is because if you were to plug in the value here inside this expression, you're going to get the negative value. So it is illogical. Okay, so in order to prove that, we can say that 0.012 plus 2 negative 0.0150. So once we put the x value into this expression, we're going to get negative 9 times 10 to the power of negative 3 molar. So at equilibrium, the concentration of Br is negative, and hence it is illogical. Tak logik untuk dapat concentration negative. Pasal concentration will never be negative, and that is why we just gonna ignore the negative 0.0105 here, and then we just gonna take the more positive value. Okay, so now once we got the value that we wanted, which is this value here, we're gonna plug into this expression at equilibrium. So for the concentration of the bromine gas at equilibrium is equal to 0.063 minus the value of x that we have obtained. So once we do the maths, we're going to get equal to 0.065 molar, which is logical. And then for the bromine atom at equilibrium, we're going to get 0.012 plus 2 multiplied by the negative 1.78 times 10 to the power of negative 3. So once we do the maths, we're going to get positive 0.084 molar. So both of the concentration at equilibrium are in the positive value. So it is logical. Okay, and that is why we take the value of x that is less negative or more positive. Okay, so this is how you calculate the concentration of the species at equilibrium step by step. So for tutorial question 11, if 0.024 mole of N2O4 is allowed to reach equilibrium with NO2 in a 0.372 liter flask at 25 degrees Celsius, we need to calculate the degree of the dissociation alpha of the N2O4. So the equation of the dissociation is given as here. So for the degree of dissociation, we know that alpha is equal to the change in concentration divided by the initial concentration. And the change in concentration is also known as X, and they're divided by the initial concentration. And since we are talking about N2O4, so we need to find the change in concentration of N2O4 as well as the initial concentration of the N2O4. And in order to find the X here, which is the change, we need to use the ice table. So for the ice table, we would need to write back the equation given, which is N2O4 gases converted to N2O2 gases, and we have the ice here, which is referred to initial, change, and equilibrium, and we're going to focus on the concentration molar here. And to get to the initial concentration, we can find the initial concentration by dividing the mole with the volume here. So the initial concentration of N2O4 is dividing mole with the volume. So the mole here is 0.024 mole and the volume is 0.372. So once we divide this, we're going to get the concentration, the initial concentration to be 0.0645 molar. Okay, and this concentration here will be plugged into the ice table here, which is 0.065, and at the initial stage our product, which is NO2, will be equal to 0, and as time goes by the concentration of the reactant will reduce by X and the concentration of the product will increase by 2x, okay, because of the stoichiometry here. And then at last, which is at equilibrium, the total concentration is going to be 0.0645 minus x, and for the product it's going to be 2x. So from here, we can write our Kc expression, and then we need to compare that with the Kc value that is given. So our Kc is equal to the concentration of the product, which is NO2 to the power of the stoichiometry 2 divided by the reactant, which is N2O4. And then our Kc here is referred to 4.61 times 10 to the power of negative 3. So we can plug in the value of NO2, which is 2x, and then we have the square, so don't forget that, divided by the expression of the reactant at equilibrium, which is 0.0645 minus x. So we can bring this term on the right hand side, and then we can expand the bracket here. Okay, so once we bring that to the right hand side, and then we're going to bring it back to the left hand side so that we can make a quadratic equation, which is ax squared plus bx plus c is equal to 0. Okay, and then from here you need to plug this value into the calculator, and then you're going to get two possible values, which is 8.064 times 10 to the power of negative 3, and then you have your x to be negative 9.217 times 10 to the power of negative 3. So in this case, we need to take the more positive value. So the more positive value will be taken, and then the negative value going to be ignored, okay, or neglected, because the negative value is illogical because we cannot get a negative concentration. So these are the x value that we're going to focus on. Okay, and from here you can straight away find the degree of the dissociation alpha. So the degree of the dissociation alpha is equal to the x, which is the change in concentration, divided by the initial concentration, which refers to the N2O4 here. So our x here is, we have obtained that, which is 8.064 times 10 to the power of negative 3, and then our initial concentration is obtained here, 0.0645 molar. So once we do the maths here, we're going to get the degree of dissociation to be 0.125 without any unit. Okay, so this is how we find the degree of dissociation. So for tutorial question 12, at 430 degrees Celsius, the equilibrium constant Kc for the reversible reaction is 4.18 times 10 to the power of negative 3. And the equation is given as here, which is hydrogen gas reacting with iodine to produce 2Hi gas. So if 0.04 mole of Hi, 0.01 mole of H2, and 0.03 mole of I2 are placed in 2-liter container, is the system at equilibrium? So we have to explain the situation. Okay, and for this reason, we need to compare our QC with Kc. Okay, so because Kc is refers to the reaction quotient at any stage of the reaction. So maybe in this case, we are talking about at the initial stage. So we need to compare whether our QC is equal to Kc or not. So if it is not equal, then the reaction here is not at equilibrium. So for this reason, we need to find the concentration of each of the species here first, because we have the number of mole. So we can find the concentration by dividing with the volume of the container. Okay, so we can find the concentration of Hi, which is mole divided by volume, 0.04 divided by 2 liter, which is 0.020 molar. The concentration of the hydrogen gas, which is 0.010 divided by 2 liter, which is 0.05 molar. And then the concentration of iodine, which is 0.03 divided by 2, where we get 0.015 molar. Okay, and then we can write our QC expression, which is QC is equal to the concentration of the product, which is Hi to the power of 2, which is the stoichiometry, divided by the concentration of each of the reactant, H2 and I2. So for the Hi value here, it refers to 0.02 square, and then for our H2, it refers to 0.05, And then for our iodine, it refers to 0.015. So once we do the maths here, we're going to get the value of QC to be 5.33. Okay, so your QC here is 5.33, but your KC here is 4.18 times 10 to the power of negative 3. So they are different. And from here, you know that your QC is bigger than your KC. So when the QC is bigger than the KC, you know that the QC is high, right? So you know that your product is very, very high. And for that reason, it needs to shift to the left in order to reduce the disturbance and so that they can make into the equilibrium state. So for this reason, the system is not at equilibrium and thus the reaction will shift to the left in order to achieve the chemical reaction at equilibrium. Okay, and the reason is as I mentioned here, because when QC is high, the numerator side, which is the product side, is high, so it needs to be shifted to the left so that it can achieve equilibrium. Okay, but to make life easier is always the reverse of this direction. So if QC is bigger than KC, then we know that it's going to be at the reverse direction, which is going to the left. All right, so that's all for tutorial question 12. So for tutorial question 13, the chloromethane is formed by the reaction of CH4 gas reacting with chlorine gas in order to produce CH3Cl as well as the HCl. So in the reaction mixture, the partial pressure of the methane, Cl, CH3, Cl, and HCl are 0.13 atm and 0.035 atm and 0.24 atm as well as 0.47 atm respectively. Okay, so please be careful with the partial pressure. So CH4 is in the rectangle box, Cl2 is in the circle form, and then CH3Cl is in the star form, and then HCl is the one underlined here. Okay, so we need to determine whether CH3Cl or CH4 is formed. So similarly as before, we need to compare our QP with our KP. And then from here, we can determine the direction of equilibrium. All right. So from here, we need to write our QP first. So QP is equal to the partial pressure of the product, which is CH3Cl with PHCl divided by the partial pressure of CH4. So the balancing of equation is 1 here. So we're going to remove that. And then the PCl2 is also to the power of 1. Alright, so from here we need to substitute into our equation. Okay, so make sure you substitute it correctly. So CH3Cl is 0.24, which is in the star form. Okay, and then HCl is underlined, which is 0.47, and then your CH4 is 0.13, and then your Cl2 is 0.035. Okay, so once you do the maths here, you're going to get your QP to be 24.79. So your QP is 24.79, but then your KP is 1.6 times 10 to the power of 4. So you know that your QP is lesser than your KP. Okay, and for that reason, the equilibrium gonna shift to the right. They must still reverse direction. Okay, so when it goes to the right, then you know that the concentration of this value and this value will get higher. So in between this one and that one, the CH3Cl gonna be formed. So you can say that at first the system is not at equilibrium. This direction gonna shift the equilibrium to the right in order to achieve the equilibrium, and more CH3Cl gonna be formed. Okay, and if conceptually you can say that when QP is low, your product side here is low, and that is why the reaction need to shift to the right in order to increase back the product here, and that is why it shift to the right. And the technique here is just to make it quick so that you know that it's going to be reversed in the direction of equilibrium. Okay, so that's all for tutorial question 13. So for tutorial question 15, the Haber process is represented by this equation. So nitrogen gas reacting with 3 mole of the hydrogen gas in order to produce 2 mole of ammonia. And this reaction here will give out energy which is negative 92.2 kilojoule. So this refers to the exothermic reaction. Okay, and its feasibility depends on choosing condition under which nitrogen and hydrogen reacts rapidly to give a high yield of ammonia. At 25 degrees Celsius and atmospheric pressure, the position of equilibrium favors the formation of ammonia. Based on the Lee-Chatelier's principle, explain how the product, which is the ammonia, could be increased. So, in order to increase the product, there are various ways we can modify the condition. So, based on the Lee-Chatelier's principle, the product can be increased when we increase the concentration of our reactant here. So, we can add more nitrogen or more hydrogen gas. So, we can increase the concentration of either of the reactant. So, when we increase the concentration of the reactant, and according to the Lee-Chatelier principle, we need to reduce our reactant back, and this will pushes the reaction to be on the right hand side, and as a result more ammonia gonna be formed. Okay, and this way can increase the amount of the product. The second thing that we can do is to remove NH3. So when we remove our ammonia, we need to increase it back according to the Lee-Chatelier's principle. So because of this, we need to shift the reaction to the right. And as a result, more ammonia gonna be formed. And the next one is we can adjust the pressure. So as what you can see here, the number of mole on the left hand side, which is on the reaction side, is 1 plus 3. So we have 4 number of mole here. On the product side, we have 2 number of mole. Okay, so from here, we can increase the pressure. So when pressure increases, we need to reduce back the pressure according to the Lee-Chatelier's principle. So it needs to shift to the less number of mole. Okay, and as a result, the concentration of ammonia gonna be increases. Okay, and you can adjust the pressure or you can decrease the volume, because when volume decreases, pressure increases, and then the same effect gonna take place. And the next thing that you can do is adjusting the temperature, because you know that this reaction here is exothermic. So exothermic reaction will releases heat to the surrounding. Okay, dia membebaskan haba. So what we can do is that we're gonna reduce the temperature. Okay, so when we reduce the temperature, it means that we're reducing the heat. And as a result, we need to increase back the heat by shifting the reaction to the right. So when the heat increases, at the same time, the ammonia will increases as well. So this is how we answer tutorial question 15. So for tutorial question 16, the decomposition of the ammonium hydrogen sulfide is an endothermic process. So the reaction goes from the ammonium hydrogen sulfide, which is in the solid state, it's going to decompose to 1 mole of ammonia gases as well as 1 mole of hydrogen sulfide. And this reaction is an endothermic reaction because it gives out energy. So it gives a positive value. So a 6.0 gram sample of solid is placed in an evacuated 4.0 liter vessel at 24 degrees Celsius. After equilibrium has been established, the total pressure inside going to be 0.709 atm. So our PT here is 0.709. Some solid of the NH4HS will remain in the vessel. So we need to find out the Kp for the reaction. Also, we need to determine the percentage of the solid that has been decomposed. So for this reason, since we are finding for the Kp, we need to know the value of the partial pressure at equilibrium. And because of this reason, we need to use the ice table, which is the initial, change, and equilibrium. And since we are talking about the partial pressure, it's going to be in the unit of atm. So at the initial stage, the concentration of the ammonia gases and the hydrogen sulfide gas going to be 0 and 0 respectively. And for the solid ammonium hydrogen sulfide, we're just going to put as a dash because solid does not involve in the Kp expression. And as time goes by, the concentration of the ammonia gas will increase by plus X, similarly for the hydrogen sulfide gas. And at equilibrium, the concentration is going to be plus X and X as well. And from here, you know that the total pressure is 0.709. And the addition of both of our gases at equilibrium, which is the ammonia as well as the hydrogen sulfide, going to be equal to 0.709. So X plus X going to be 0.709 atm according to the Dalton's law. So we have 2x is equal to 0.709, and then our x here going to be 0.3545 atm respectively. And from here, you can find out the Kp expression by writing out the Kp expression first, which is the partial pressure of the ammonia multiplied by the partial pressure of the H2S. And for the partial pressure of NH4HS, it is not included because it is in the solid state. So we're just going to ignore that. Okay, so it's equal to x and x, where x value here is 0.3545. And then when we do the maths here, we're going to get 0.1257. So the Kp here going to be 0.1257 without any unit. Okay, because in this chapter, Kp is treated to be dimensionless. Alright. Now we're going to move on to the determination for the percentage of the solid that has been decomposed. So for the percentage of dissociation, we need to use the value of alpha. So alpha is equal to the change in concentration divided by the change by the concentration at the initial stage. And since we are talking about percentage, we need to multiply it by 100%. Of course, we can also use the mole, which is the change in mole divided by the mole at the initial stage, which refers to NH4HS. Okay, because concentration is directly proportional to the number of mole. So we can use either one of these in order to find out the percentage of the solid that has been decomposed. So here is the equation that we have written it again. And then from the ice table, we know that the concentration of the partial pressure of the NH3 is 0.3545. And from here, we can find out the number of mole of ammonia first, in which we can use the ideal gas equation because we have the volume and we have the temperature, in which we need to convert that into Kelvin by adding with 273.15. So we know that PV is equal to nRT, and since we are talking about ammonia, so we need to specify that. And we can find the number of mole of ammonia by dividing PV with RT. So our P here is 0.3545, our volume is 4 liter, and then our R here is the gas constant, and then T here is the temperature in Kelvin. Alright, so at last, once we do the math, we're going to get the mole going to be 0.05815 mole. And from the equation, you know that 1 mole of ammonia will produce 1 mole of NH4HS. So you can equate that. It is also equal to 0.05815 mole of NH4HS. Alright, and here refers to the change in the mole, which is this part here. And you can also find the initial number of mole, because you know that initially it started off with 6.8 gram of the sample. So this is the initial number of mole. Okay, so the mass divided by the molar mass, which is 14 plus 4 plus 1 plus 32 gram per mole. So once you do the maths here, you're going to get the number of mole initially for the NH4HS going to be 0.1333 mole. And you can find the percentage of dissociation, where X here refers to the mole, which is change in the number of mole, and then here is the mole at the initial stage. Okay, so it's gonna be 0.05815 divided by the initial, which is 0.133, and we need to multiply by 100% because we are referring to the percentage that has been decomposed. So once we do the maths, we're gonna get the alpha gonna be 43.62%. Alright, so this is how we answer the question for the degree of dissociation. Now, for the last part here, if the volume of the vessel were doubled, okay, sekiranya volume dinaikkan sebanyak 2 kali ganda at constant temperature, what will happen to the amount of solid in the vessel? So we need to find the amount of the solid, and we need to find out what happened to the degree of the dissociation. And from here, when you know that the volume is increases by 2 times, we know that the pressure going to be reduced by half. Okay, so we can see that if the volume of the vessel is increased, which is double, the pressure will be decreased by half. And as a result, when the pressure decreases, the equilibrium will shift to the side with a higher number of mole. So from here, it doesn't have any number of mole that is related to the gaseous. Okay, so we have 0 number of mole for the gaseous state. From here, we have 2 number of mole because we have 1 here and then 1 here that is related to the gaseous. And because you know that when the pressure decreases, we need to increase back the pressure by going to the side with a higher number of mole. So it needs to go to the right hand side. And hence we can say that the direction of equilibrium shift to the right, and we can say that more NH4HS going to be dissociated in order to produce NH3 and H2S, and therefore the amount of the solid will decrease in the vessel. Okay, and because there is more NH4HS that is being dissociated, it means that the value of X here will get higher and higher because lagi banyak dia akan terurai untuk membentuk NH3 and H2S. And as a result, the alpha will also increases because alpha is related with X. So when X increases because of the dissociation, alpha gonna be increases as well for the degree of the dissociation. Okay, so this is how we answer question number 16. So I think that's all for today's video. See you again some other time. Bye.